Okay, so now that we've talked a little bit about the different types of bonds that form, so ionic versus covalent, and we've talked a little bit about how to tell what type of bond has formed in a molecule, whether it's covalent, polar covalent, ionic, those different things based on the electronegativity difference. When we put all of that together in an overall molecule, those factors affect what the actual molecule shape is going to be. And when we talk about the types of molecules we're dealing with in biology, that shape determines its function. So I want to spend a little bit of time today looking at the different possible shapes you can have in a molecule and why it is the way it is. So it has to do with three things, and that is the first of all, the type of bonds, the overall shape, and the polarity. So we'll deal with each of these. So there's something called the Vesper theory. For any of you that have taken grade 11 chemistry, this also might be a review for you. If you haven't taken any chemistry courses past grade 10, this might be new information to you, and I might suggest that you consult our textbook that I've posted as well, just for anything extra, because I will go through this fairly quickly, as this is supposed to be a little bit of review. So the Vesper theory stands for valence shell electron pair repulsion. So we talked about what valence electrons are. Those are those electrons on the outermost shell. When we have some of those electrons in the outermost shell left that are not paired up or forming a bond with something, something special happens. Those negative electrons will repel each other and want to move as far apart as possible. So considering that, based on that theory, there's 4 different possible shapes that you can end up with based on this. So the first shape is tetrahedral, and we're just going to go through and draw some examples of these so you can kind of get a feel for them, but your textbook also has a good breakdown of this. So an example of a tetrahedral molecule is when carbon comes together with chlorine. And carbon has 4 bonding spots, and chlorine needs to pair up with 1. So we need 4 chlorines, right, to satisfy each of these 4 bonding spots. So what happens when chlorine and carbon come together is it forms a shape called tetrahedral. So we'll draw it first and then I'll explain it. So we have carbon in the center bonded to a chlorine, chlorine, now, the tough thing is that we're trying to draw something 3-dimensional on a flat piece of paper, so you kind of have to imagine here. So since all of carbon's valence shell electrons are satisfied because they've all paired up with chlorine's single electron that needed to be paired, there's no remaining electrons surrounding carbon. So what happens is each of these chlorines spread out equally surrounding this carbon atom, and what we end up with is an angle between each of these bonds of 0.5 degrees, and that's equally spaced, each of them, because they're going to spread out equally. If we consider the example of, let's say, nitrogen coming together with hydrogen. I'm going to use a different color here. If we think about nitrogen, it's got 2 paired at the top and then 3 singles that need pairing, and hydrogen has that single one to pair. Okay, so there's 3 spots the hydrogen can come in. So we end up with a molecule, a hydrogen coming off here, hydrogen coming off here, and a hydrogen coming off here. Because we have these 2 pairs of electrons that have not formed a bond, this is where the Vesper theory comes in. And these electrons repel each other, which eventually end up pushing these hydrogens away, forming what we call the pyramidal shape. Okay, so the bond angles in this example, because they're squished down a little bit more than they were with the carbon and chlorine, we end up with a bond angle of 107 degrees. Here and here. And that forms what we call the pyramidal shape. Okay, the two remaining shapes. Angular is the next shape, and we're going to look at an example of when oxygen and hydrogen come together. So oxygen has 1, 2, 3, 4, 5, and 6 valence shell electrons, 2 pairs and then 2 singles, and hydrogen has that one. So when oxygen and hydrogen come together, you're going to have 2 hydrogens bonded to oxygen in those 2 spots. So if you picture these 2 pairs of electrons are not forming a bond with anything. So if you think of the VSEPR theory, these are going to repel each other and push, just like in the last example, they're going to squish these other 2 bonds closer together as well. And so what we end up with is an even smaller angle between these 2 bonds of 104 degrees. And that gives you your angular shape. And so the last one is linear. Linear means a straight line. So we can look at an example, hydrogen and chlorine. When hydrogen and chlorine come together, chlorine has 7, so 1 unpaired, and hydrogen has 1 unpaired. So we just need 1 of each to satisfy that full outer shell. So hydrogen's going to come straight in and bond with chlorine in a straight line, giving us this angle of 180 degrees. Now, for the actual shapes, because I've just demonstrated why the angles end up the way they are, have a look in your textbook. They've done a better job of giving you the 3-dimensional view of each of these types of shapes, because this definitely does not do it justice. Okay, so next, we talked a little bit about the polarity of a molecule. When we just looked at 2 elements coming together to form a bond, we could use the periodic table, their electronegativity differences, to figure out if the bond was polar, just between those 2 elements. Now, if we consider an entire molecule of a certain compound, we're going to take 2 things into effect. We're going to look at the overall shape, but also the electronegativity differences, because they can actually affect the overall polarity. So now we're thinking of an entire molecule, not just a bond. Okay, so we're going to look at the 2 different examples that you might encounter. So the first example, bonds are polar, but equal distribution of charge, therefore equals a nonpolar overall molecule. So we'll go through an example and hopefully this will make sense. So if we look at the example of carbon with chlorine, we know it forms this tetrahedral shape. And if we go back to what we learned about yesterday with the electronegativity differences, and I'm not going to use numbers, I'm just going to show you our positives and negatives in terms of electronegativity. So the chlorine, all the chlorines have a partial negative charge. Remember, this is the symbol, just means partial. So all these guys have a partial negative charge. And in relation or relative to that, carbon has a partial positive charge based on their electronegativity values. Now, because their shape, it can actually cancel out the overall polarity of a molecule. So yesterday I told you when you have just 2 elements that come together and form a bond, you can end up with a partial negative side to that and a partial positive side to that. But when we now think about the overall shape, if these negative charges distribute themselves evenly around that positive charge, they essentially cancel each other out. So if you think of this molecule as a whole, you don't have an end of a molecule that's positive and an end that's negative, because all of these negatives surrounding this positive, equally spaced, cancel out. They cancel each other out. So that's why when we look at this entire molecule, we can call it nonpolar. So bonds are polar. Each of these bonds are polar because one side's negative, one side's positive, one side's negative, one side's positive. But the entire molecule itself is nonpolar because these guys are spread out equally surrounding that positive charge. So the other example we can have is that the bonds are polar, just like they were here, but they're not distributed evenly around the molecule or around the central element. So we end up with polar, because remember I said polar means that we have a positive end and a negative end to it. So if we use nitrogen bonded with our 3 hydrogens, we end up seeing that nitrogen has a partial negative charge, and these 3 hydrogens have a partial positive charge. Now, in this example, the surrounding elements cancel the central one out. But remember the VSEPR theory, these 2 electrons push these bonds down a little bit. So if you look at the distribution of this, we can draw a straight line sort of through our molecule, and on one side of that straight line we have a partial negative side, and on the other side of it we have mostly partial positive charges. So if we can draw a straight line through a molecule with negatives on one side, positives on the other, that makes it polar. Remember I said in our bonds yesterday that if one side was negative, one side was positive, it's called a polar bond. Same thing happens with the overall molecule. Okay,